Ever wondered how a single cable between two switches can carry traffic for dozens of separate VLANs without mixing them up? Welcome to Stage 2, Lesson 10 of our networking curriculum. Today we're diving into 802.1q tagging, the standard that makes trunk links possible, and the key to understanding how modern switched networks actually keep VLAN traffic organized over shared wires. Here's the roadmap for the next few minutes. We'll start by cracking open an 802.1q tag and looking at it byte by byte so you can see exactly what gets inserted into a frame. From there, we'll talk about the native VLAN, the one VLAN on every trunk that travels untagged, and why that detail matters. Then we'll cover DTP, Cisco's dynamic trunking protocol, and why most engineers turn it off. And finally, we'll connect all of that to a real attack, VLAN hopping. So let's start by cracking open a frame. A regular Ethernet frame has destination MAC, source MAC, either type payload, and the frame check sequence at the end. When a switch sends that frame out a trunk port, it slips a 4-byte 802.1q tag right between the source MAC and the ether type. That's the only structural change. Those 4 extra bytes push the maximum frame size from 1518 up to 1522, which Cisco affectionately calls baby giants. 2 important details. The tag is added by the sending switch and stripped by the receiving switch before the frame hits an access port, so end hosts never actually see VLAN tags. And historically, before 802.1q became the IEEE standard in 1998, Cisco used its own 40-byte ISL encapsulation. You'll still hear the name, but in practice, everything today is .1q. Now let's actually open up those 4 bytes. The first 2 are the TPID, always set to 0s8100. That's the flag that tells any switch reading the frame, hey, this is VLAN tagged. The next 2 bytes are the TCI, which splits into 3 fields. PCP, 3 bits for priority. That's your quality of service marking, 0 through 7. DEI, a single drop-eligible bit. And finally, the star of the show, the 12-bit VLAN ID. 12 bits gives you values 1 through 4094, and that's the field switches actually look at to decide which VLAN this frame belongs to. So where does that tag actually get added and removed? Here's the key insight. The hosts themselves never touch VLAN tags. Host A just sends a plain Ethernet frame onto its access port. Switch A sees that frame arrive on a port configured for VLAN 10, so it inserts the 802.1q tag with vid equals 10 before sending it across the trunk. Switch B receives the tagged frame, reads the VLAN ID, figures out which access port belongs to VLAN 10, strips the tag back off, and delivers a clean untagged frame to host B. Tagging lives entirely between the switches. It's transparent to the endpoints. Now here's a quirk worth knowing about. Every trunk has one special VLAN called the native VLAN, and its frames travel across the trunk completely untagged. This exists for backwards compatibility. Older devices that don't understand 802.1q can still hop onto a trunk link, and the receiving switch just assumes any untagged frame it sees belongs to the native VLAN. But this is also where security gets interesting. Best practice, never leave it as VLAN 1. Always match it on both ends to avoid cross-VLAN leakage, and ideally, force tagging on the native VLAN 2 with VLAN.1q tag native that closes off a classic VLAN hopping attack surface entirely. Let's put all of that into actual configuration. We drop into the interface, force the port into trunk mode, and explicitly set the encapsulation to .1q. On modern switches, this is the only choice, but it's good habit to declare it. Then we apply the 2 security hardening steps we just talked about, prune the allowed VLAN list down to only what really needs to cross, and move the native VLAN off of 1 to something unused like 99. Finally, show interface's trunk confirms the port is actually trunking, what encapsulation it negotiated, and which VLANs are permitted across the link. Now, how does a Cisco port decide on its own whether to become a trunk? That's the job of DTP, the dynamic trunking protocol. There are 4 modes: hard-coded access, never trunks, hard-coded trunk always trunks, and the two dynamic modes negotiate. Desirable actively asks, while auto just waits and accepts. The problem is that dynamic auto is the default on many Cisco ports, meaning any device that speaks DTP can talk a port into trunking. The fix is simple. Hardcode the mode you want, then shut DTP off entirely with switch port non-negotiate. And as we'll see next, that default is more than just untidy. It's a real attack vector. And here are those attack vectors in action. The first is switch spoofing. An attacker plugs in, sends crafted DTP frames pretending to be a switch, and the real switch happily forms a trunk. Suddenly, the attacker sees every VLAN crossing that link. Game over. The second is sneakier, double tagging. The attacker builds a frame with two 800.21q tags stacked. Outer tag matching the native VLAN, inner tag pointing at the target. The first switch strips the outer tag because native VLAN traffic is untagged on the trunk, then forwards the frame. The second switch sees only the inner tag and dutifully delivers it into the target VLAN. The frame has hopped. The fix, force, native VLAN tagging with VLAN.guangqiu tag native, and the trick falls apart. Now let's get practical. When trunks misbehave, these are the patterns you'll see in the wild. Two hosts in the same VLAN on different switches can't reach each other. Run show interfaces trunk and check the allowed list. Odds are that VLAN got pruned. Logs flooded with native VLAN mismatch warnings means the two ends disagree on which VLAN is untagged. So align them. A trunk mysteriously forming with a user's laptop, that's DTP doing its thing on a dynamic auto port. Lock it down with switch port mode access and switch port non-negotiate. CPU spiking from broadcast storms usually means your trunk is allowing every VLAN under the sun. Trim that list. And if the VLAN exists but nothing passes, check that the trunk is actually up and the encapsulation matches on both sides. Now here's a fascinating exception to the access versus trunk rule we've been building up, the voice VLAN. Picture a typical office. A single cable runs from the switch to an IP phone, and the user's PZ plugs into the back of that phone. One cable, but two devices that need to live in different VLANs for QoS and security reasons. The switch port is configured as access, but with two VLANs assigned, VLAN 10 for data, VLAN 40 for voice. The phone learns its voice, VLAN through CDP or LLDP, then tags its own traffic with VLAN 40, while passing the PC's untagged frames straight through. The switch sees tagged frames and puts them in voice. Untagged frames go to the access VLAN, technically not a real trunk, but functionally two VLANs on one wire, a clean compromise that saves cabling everywhere. So let's tie everything together. 5 things to carry with you from this lesson. First, the 802.1q tag is just 4 bytes, a TPID of 0x8100, a priority field, the DEI bit, and 12 bits of VLAN ID. Second, trunks carry many VLANs tagged. Access ports carry one VLAN untagged. Third, the native VLAN is the single untagged VLAN on a trunk, and it must match on both ends. Fourth, always hardcode the mode and turn off negotiation. Leaving DTP on is a real security risk. And fifth, voice VLANs let one port serve two VLANs, with the phone learning its assignment through CDP or LLDP. Here's your cheat sheet. Keep this one handy. The tag itself breaks down into TPID, PCP, DEI, and VID. The port modes split cleanly into trunk and access. The native VLAN is your untagged exception. DTP is the feature you disable with non-negotiate. And VLAN hopping is the attack that exploits either DTP or double tagging. Screenshot it, print it, tape it to your monitor, whatever works. And that wraps up trunking. But here's the thing. You've now got VLANs that are completely isolated from each other, which is great for segmentation, but useless if hosts actually need to talk across them. So in Lesson 11, we'll tackle inter-VLAN routing, how to connect those separated networks using either router on a stick or switched virtual interfaces. I'll see you in the next one.